Okay, well, hello, and thank you for joining me. And oh dear, I just clicked something on my phone. Okay, I have posted. All right, so it's only the second week, but we should start talking about the midterm exam because we have a midterm exam in 1 week on third week Thursday. So the midterm exam will be in a week, August 18th. And the exam is an hour 50 and will be held in person. Yeah, if you can't come, let me know as soon as possible. We'll try to make arrangements, and don't come if you are sick. Okay, so we want to stay healthy here. All right, and our classroom is I don't know where everybody has been when we have class. So I think it's gonna be crowded on midterm day. So please, we're gonna follow the health and safety protocols. Please wear your mask and all of that. Okay. I posted a file on Canvas. It is right here under week 2, midterm topics. I think this is it. And okay. And so this is important. Don't share this file. Don't share this file with other people, right? And then midterm, for the midterm exam, you can have one full sheet of notes, regular size, 8.5 by 11. Okay, so no giant newspapers. One full sheet of notes. You can have writing or typing on the front and back. And oh, bring your calculator. You'll definitely need a calculator. Maybe I should write that somewhere. But make sure you bring a calculator as well. And so these are the topics, and you can kind of discuss them on Campus Wire or wherever. Give each other practice problems, stuff like that. Okay. No, it's not single-sided. You can write on the front and back for your note sheet. I don't like to call it a cheat sheet because I don't like to imply that this is any kind of cheating or anything. This is completely sanctioned by me. I want you to bring in some notes. And I think it's actually helpful when you create a sheet of notes for yourself, like you have to think about what you're going to include. In general, I recommend creating the notes, like either typing it yourself or writing it out by hand, rather than, I know some people, and you're allowed to do this, I'm not going to stop you, but you can, like, some people take screenshots of the notes and they shrink them down and they kind of create a sheet of notes that way. I think there's something that is good for your brain as far as the learning goes, where you like write it out by hand and stuff, and you create examples for yourself, and I think that's good. But I can't, you do whatever you want. Okay, so it can be handwritten or typed. So that's what we have. Okay, let's see. What else? Anything else I need to say? I'll talk. I guess I can talk a little bit more about it on Tuesday as well. But I wanted to kind of just throw it out there right now, so that you can start preparing and studying for the exam. And if you look at kind of the list of topics that I put on here, a lot of it we've already covered. Okay, so vector-based gradients, we've done that. Gradient descent, we've done that. Regularized loss, we've done that. Leave one out, cross-validation, we've done that. Okay, the only thing we haven't done is neural networks, but numeric gradient calculation, we've also already done that. And so today I'm going to kind of introduce kind of a neural network, some ideas here, but pretty much we've covered all of these things. And it's also covered in your homework this week, and you can get started on, I guess next week I'll post another homework, but pretty much everything, even the numeric gradient calculation we've covered. We just haven't really, today I'll show you kind of the structure of a neural network and stuff, but you can start studying all of these things. So So we have that. Okay. All right. Well, let's take a look at today's material, which I'm going to cover a few things: more regularization, and we'll talk about the bias-variance trade-off, and then I will also introduce neural networks today. So lots of stuff here. Okay. So we talked about regularized loss. So for lasso and ridge regression. And we said that for this stuff to, the way it works is that our loss function for the regularized thing combines the regular OLS loss function plus blank. And what does it add to the OLS loss function? Complexity, exactly, right? It combines the OLS loss function plus a penalty for complexity. So as complexity goes up, this penalty also goes up. Okay, and then what do we have? What term do we use to determine which goal has greater priority here? We have a lambda term, right? Okay. Yeah, you got it. Okay. So we combine the, so these are the answers. The lambda term, I guess sometimes it's a gamma, but usually a lambda term will decide whether the reduction in complexity is more important or whether the reduction in OLS loss is more important and things like that. And okay, so this is what we have. The OLS loss is this plus some lambda times some complexity penalty here. And for lasso, the complexity penalty is the absolute values of the coefficients in W. And then for ridge regression, the penalty is the sum of squared values in the ridge regression. Okay. And there is kind of something called elastic net, which is, a hybrid of these two. Okay. And this one says, you know what, let's have a absolute value penalty mixed with a squared error penalty. And kind of, if you have alpha here, we have two mixing terms. So, or two parameters here. Lambda is overall how much the penalty counts, the complexity penalty is. And then the alpha is which of these do we weight more? Okay. So if we have alpha, if alpha is equal to 1, then it's just lasso, right? Because alpha equal to 1, then we have the absolute value, and then this becomes 0, and we have no ridge regression. And then if we have alpha equal to 0, then we have no absolute value penalty. This is 1, and we just basically have the ridge regression penalty pretty much. Okay. So alpha 0 to 1 and alpha 0.5 is like halfway in between, and it's kind of just like a knob. Like, do you want it more this way or more the other way? It's kind of some kind of you can turn the dial and decide which of these things you want to stress. Okay. And this is implemented in R with a package called glmnet, and you can read more about it here. And this is quoted directly from the description, and it says, it is known that the ridge penalty shrinks the coefficients of correlated predictors towards each other, right? And we saw that, right? We saw the on Tuesday, as I increased the thing, we saw the parameters, kind of the W2 and W1 parameter that went towards that line y equals x. So it started off in the middle of the ellipse, and then it went towards the line y equals x, and then it started shrinking towards 0. Okay. Whereas lasso tends to pick one of them and discard the others. And we saw that with lasso, it went until one of the parameters turned into 0. And then, and that's what we have. It says the elastic net penalty mixes these two. If predictors are correlated in groups and alpha equals 0.5, then tends to select kind of parameters that groups in or out together. This is a higher level parameter, and users might pick a value up front or experiment with a few different values. Okay. And then also, because lasso itself tends to push some coefficients down to 0, it can be used for variable selection. So how do we do this? Well, ElasticNet has been implemented in package GLMNet. Also, if you took 101C with me, I guess just a couple of weeks ago, you might have played around a little bit with GLMNet as well in tidy models. But here we'll just take a look at kind of base GLMNet without getting into tidy model stuff. And so in order to kind of use GLMNet, you have to break up your values into a matrix of predictors X and a matrix, a column matrix of the outcome values Y. It defaults to having alpha equal to 1, which is basically lasso. And you would just kind of fit, you call GLMNet on X and Y, and it's going to do some work here. Okay. So what I've done here is I created some artificial data, and in our artificial data, there are 4 variables: X1, X2, X3, and X4. X1 and X2 are correlated. X3 and X4 are correlated. And, X1 is independent of X3 and X4, and X2 is also independent of X3 and X4. And what's actually happening is the true value of Y depends only on X1 and only on X3, okay? And the coefficient for X1 is 3, and the coefficient for X3 is 1.8. So the true value of Y only depends on X1 and X3, but then we add some noise here. And because X1 and X2 are correlated, it might look like there's a relationship between Y and X2. And because X3 and X4 are correlated, it might look like there's a relationship between Y and X4. But the true value of Y only depends on X1 and X3, okay? All right, and so here I call GLMNet to fit a lasso model to this data. And here it goes. Okay. And I think on Tuesday, someone had asked, how do we figure out what lambda value to use? And well, generally the answer is you don't try to figure this out yourself. You use some form of cross-validation, or you do use some kind of grid search. Okay, and so you'll just test out a whole bunch of different lambda values, and then you see how your model performs with all of these different lambda values. And if you are using tidy models, you can kind of do a grid search. You create a tuning grid, and it does that. GLMNet also implements basically a grid search here for you. And so when you call GLMNet on X and Y, it automatically tests out a whole bunch of different lambda values. So it just tries them out, 3, 2, 2.5, whatever. Tries out a whole bunch of different lambda values, and it says, well, okay, this is kind of its performance here for all of these different lambda values. And so the results are shown as a listing with 3 columns. The first column here is the degrees of freedom, and this is effectively kind of the number of variables that we've used in the model. So here, if you look at this, it says you've used no models. Or no variables. And here, these are models with 1 variable. These are models with 2 variables. Okay, all of these have 2 variables. And here we're all kind of reducing lambda to a lower value that allows basically for larger coefficients. This middle column is the percent of deviation explained. It's pretty much the R² value for this model. So if you're using no predictors, your R² value is pretty much 0. And as you increase, allow for, I guess, less lambda, have less complexity parameter, your R² value goes up, okay? And here is the last column is the value of lambda used by GLMNet. So when lambda is large, model complexity is punished greatly, and this is going to push all the coefficients down to 0. And at the very end, you have or at the very top, you have degrees of freedom 0, meaning we are using no X predictors here. And then as lambda decreases, the models are punished less for complexity. And this allows us to kind of incorporate more terms, and we're able to, our R-squared value goes up. Okay. If you calculate, whoops, I don't know where this number came from. The R-squared value for OLS is 0.954. Okay, 0.954, and that would be the coefficients if you use all of the terms x1, x2, x3, and x4. Okay, and we notice the coefficients for x2 is close to 0. The coefficient for x4 is also close to 0. Sorry, this is a typo. I must have written something from somewhere else. Okay, but our R-squared is something around 0.954 here. Okay, and what we can see is basically our R-squared value goes down as we increase our lambda. Okay, and basically when we have lambda equal to 0, we're going to get 0.954. The coefficients in lambda are stored, or I'm sorry, in the coefficients that it estimates for the different terms, x1, x2, x3, x4, and stuff, they're stored in a matrix called beta. And this is a sparse matrix, so meaning it only stores values where it's not 0. And basically, if you see a little dot in the sparse matrix, it means it's a 0. Now you can take this sparse matrix and you can call as.matrix, and R is going to fill in zeros. So you can see these things, these numbers and these numbers are all exactly the same, except here it's filled in the dots with zeros here. Okay, so so you can kind of, so this actually is visually easier because you don't have, your eyes don't have to like factor in that these are all zeros and stuff. But if you need to like work with it mathematically, you'll probably need to turn it into a matrix and stuff. All right, and so what we can see is that for some of these, as we look at the coefficients, all of these the values that we have over here are get very close to kind of the OLS coefficients, and we see that the coefficients for x2 and x4 are actually very close to 0 to kind of start off with. Okay, and so even at the very end, when we have tiny a very small lambda, which is basically what's happening over here, actually the coefficients for x2 and x4 still get kind of pushed down to 0 as well. If you want, you can ask for the coefficients for a particular value of lambda. And so you can say, I want the coefficients of the fitted thing, and you specify it for lambda equal to 0.2, and these are the numbers. Here it is for lambda equal to 1, and you get different numbers as well. And so you can see with a larger lambda, the coefficients are shrunk a little bit more, okay? So that because there's a greater penalty for larger absolute values, so these values get shrunk a little bit, okay? With when we have a larger lambda. All right, so how do we pick what lambda we should use, okay? Well, there is a cross-validation feature built into GLMNet. Okay, and so again, if you're familiar with tidy models has a bunch of kind of cross-validation features built in, and if you've never used tidy models, that's also okay. There are some cross-validation features built into GLMNet, and the idea here is you do cross-validation, so you pick some lambda value, and using that lambda value, you fit the model, and you get coefficients, but you've split the data into training and validation. Okay, so you split the data into, maybe several different folds, and if it's 4-fold cross-validation, you're going to use 3 of those folds for the training. You estimate your coefficients based on the training data, and then you predict values on the validation set, and then you do this 4 different times. Or here I've done, I guess, 5 folds using cross-validation, and we fit it for lambda with lambda equal to some value, lambda equal to some other value. Okay, and I guess over here it's the log of lambda, so basically lambda equal to 2 point something, and here would be lambda equal to 1. The log of lambda is 0, and the lambda values keep getting smaller and smaller. And we can see what is kind of our mean squared error from cross-validation for these different values of lambda. And when we run glmnet here, it says, okay, you know what? And it's kind of hard to see, but the lowest value for lambda, or lowest value for the mean squared error, happens at this line right here, at this line -3. Okay, and if you look really closely here, so I don't know how to, so this is the lowest value, and these other values over here are a little bit higher. Okay, but there's like a little bit of a standard error, and so what it's saying is that this is the lowest right here, but here's a lambda value where it's a little bit higher, but the amount of error at this dot is within 1 standard error of this. Okay, so that's kind of, if you use glmnet, that's kind of its rough guide for how do you pick a lambda. It says, you know what, obviously we want the lambda that's going to minimize the mean squared error, but we also we kind of want a slightly larger lambda. We want the largest lambda that doesn't really mess up our predictions, because if we pick too large of a lambda, then we've penalized the complexity too much, and we have a model that doesn't perform well. But if you have too small of a lambda, you're not punishing or penalizing complexity at all, and you might get a model that overfits. And so you want something that kind of in between. And so kind of the recommendation is look at the smallest lambda, look at the standard error on that, on its estimate, the mean squared error, and then pick another lambda, a larger lambda that still produces errors within 1 standard error of this. Okay, and so this is, so that you end up getting a lambda around here. So you can ask for what was the lambda that corresponds to the minimum. The minimum lambda was this 0.05, lambda.min. You can also say what was the lambda that was within 1 standard error, and the lambda that was within 1 standard error is, I guess, 0.269. Okay, and that's the kind of recommended value. So lambda min is the value of the lambda that produces the smallest cross-validation mean squared error, but it's got a standard error because it's subject to the random nature of the train and test splits. And so lambda 1 SE is a larger value of lambda that still produced small cross-validation mean squared error. Okay, that would be kind of the lambda that we pick. Okay, and why are we bothering with all of this regularization? Okay, well, this gets to the bias-variance tradeoff, And so when we fit a model to observe data, the coefficients that we estimate are subject to the random noise, right? There's random noise, there's a true relationship, but there's also random noise in the data. And so, if we took another random sample from the population, we would get similar coefficients, but also different coefficients. And OLS says these produced the best linear unbiased estimators. And I think you kind of proved this in one of your classes, maybe 100C or 100B or something like that. And basically what that means is that, the coefficients estimates of OLS are unbiased. That means in the long run, if you keep doing this thing of taking different random samples and estimating the OLS coefficients every single time, in the long run, the average of all of those different OLS coefficients will be equal to the true coefficients in the population. So if there is some true relationship, some true value in the population, in the long run, OLS will get it, okay? And the best here means that there's the lowest amount of variance. As far as among all other estimators that are unbiased in the long run, OLS also has the lowest amount of variance. So this is the best linear unbiased estimators, okay? But we also know if certain variables are highly correlated, the coefficients of these variables exhibit high variance, right? And that's kind of the problem with collinearity. And that's something that, they teach you in 101A, things to watch out for. And if you want to improve your predictive performance, then watch out for collinearity. So what lasso and ridge and these regularization methods do is it says, you know what, let's try to reduce the variation, okay? Let's reduce the variation further, okay? But the OLS estimates are already the best, the ones that produce the least amount of variance, right? Can you reduce the variance even further? Yes, we can. It's just that they are no longer unbiased, okay? So we introduce bias. And so in the long run, after fitting a lot of random sets, the lasso and ridge regression coefficients will have bias. Those expected values, the expected value of lasso fit to a whole bunch of random samples will not be equal to the true coefficients. So that's a drawback. But the benefit is that we have less variance. And so you don't have to worry as much about random noise messing up your estimates. Okay, so having less variance is a desirable trait, okay? And it means that the coefficients, the model estimates that you get are less likely to be swayed by kind of the random noise that exists in the data, right? So again, if I were to conduct an experiment and you were to conduct the same experiment, and we both took random samples of data and we both fit basically the same model, I fit the same model to my data, you fit the exact same model to your data, we're hoping our results match. But if my coefficients are drastically different from your coefficients, then that's worrisome. Now we're like, well, whose coefficients are right? Okay. And yeah, sure, in the long run, if we have a whole bunch of data, our coefficients, the average of all of our coefficients will be correct. But kind of in the meantime, right now, I've got coefficients and they look a lot different from your coefficients. And this is worrisome, right? We want results that kind of are similar and match each other. And when we have a high variance between our coefficient estimates, that's a little bit worrisome. On the other hand, if the coefficients for a model change very little with different random samples, like, right, we do an experiment, I get my coefficients, you do the same experiment with a different random sample and you fit the same model and you get a set of coefficients, and your coefficients and my coefficients, sure, they're not exactly the same, but they line up very closely, then we feel pretty good, right? So low variance for coefficients, that's a desirable trait. We want that. So here is a little simulation showing how lasso and ridge regression produce coefficient estimates that have lower variance, but at the cost of having bias. Okay, so what are we doing here? We have, we're going to have x1 and x2 are related, x3 and x4 are also related. The true relationship between y and our x matrix is that y depends on x1 and y depends on x3, but not on x2 and not on x4. But x1 and x2 have correlation of 0.85, and x3 and x4 have correlation of 0.85. And so we're going to draw, so I'm generating data here. We're going to draw random samples with a kind of a for loop. And with each loop, we generate different random noise. And the random noise is generated to the values of y. And this is going to simulate basically just random samples drawn from the population. And what we will do is we will use GLMNet's cross-validation to select the model with the largest lambda that's within one standard error of the minimum lambda. So we'll pick the lambda 1 SC. And we're going to store all of the coefficients that we have, okay? We're going to have the OLS coefficients, the lasso coefficients, and the ridge regression coefficients. Okay, so let's see what happens, okay? So again, with each loop, I'm adding random noise. And so we're going to get slightly different values of y, okay? And then I fit OLS model, and I store those coefficients. I'm going to fit cross-validation. I'm going to fit GLMNet. Okay, this is a lasso model, and then we're going to take the coefficients from that lasso model, the one with the lambda 1 SC, and we will store those. And then we do the same thing. We fit GLMNet alpha equal to 0. This is a ridge regression model. And we are going to store the coefficients from ridge regression and store those. Okay, and we do this, I guess, 100 times. 100 times. Oh, all right. Before I forget, let me give you your first view quiz answer. The first view quiz answer is the letter D. D as in dog. D as in dog is the first view quiz answer. D. D as in dog. Okay, so this is the sampling distribution for the different coefficients. So the true value of x1 in the population is 3. The true value of x1 in the population is 3. And OLS, we can see for different random samples, in the long run, they're centered at 3. Sometimes we get values above 3, 3.5, 3.6. Sometimes we get values lower than that, 2.5, 2.4. But in the long run, it's centered at 3. Okay, our OLS coefficients are centered at 3. What about lasso? Okay, in lasso, they're centered maybe around 2.65, 2.7. So they are biased. Okay, the true value is 3. And we're getting something centered around 2.65-ish, okay? But how much variance do we have? Okay, let's look at, I'd say, 95% of our data, 95% of our coefficients in OLS are between 2.5 and 3.5, okay? And here I would estimate eyeball 95% fitting between 2.4 and 3.0, okay? So the range on the middle 95% is around 1.0 for here. And the range on the middle 95% for lasso is only around 0.6. Okay, so we reduced the variance, reduced our variance in the coefficients here. Okay, ridge regression, it's centered maybe closer to 2.25. Okay, 2.25. So quite a bit different from the true value of 3.0. Lasso introduces some bias. Ridge regression seems to introduce even more bias here. And I would say the middle 95% maybe goes, 1.9, 2.0 to 2.6 or 2.7. So, a little bit more variance than lasso, I would say, but less than OLS. So here we go. Okay, so the true relationship has a coefficient of 3. And if we look at the average of all of the OLS coefficients, we have an average of something right around 3, 2.997. So that indicates that, yeah, OLS is unbiased. We can ask, what's the variance? The variance is 0.06, 0.0636. So another way of kind of measuring how much variance there is. The variance of that model is 0.0636. Okay. What about for lasso? The average of the lasso is, yeah, around 2.68, it says, the mean of lasso. So there's some variance there. I mean, some bias there, not quite 3, less than 3, 2.68. But the amount of variance is a lot less. The amount of variance is like half of this, right? 0.0636. Here we're at 0.34, 0.034. Okay. For ridge regression, we've got more bias. Its average is around 2.26. So a bit more different from 3 than lasso. And it has a bit more variation than lasso. Lasso had a variation of around 0.03. Here we have variation of around 0.04. Okay, so this just kind of sums up what we saw here. So that's for the x1 coefficient. What about the x2 coefficient? So the x2 coefficient, if you remember the generation of the data, y has no relationship with x2. Y has no relationship with x2. Okay, x2 is correlated to x1. But y has no relationship with x2. To generate our y values, we use the x1 value and the x3 value, but nothing from x2. So the true value of x2 is 0. The true coefficient for x2 is 0. Okay, so if you look at OLS, yeah, it's centered at 0. But sometimes it estimates the coefficient for x2 as low as -1. Sometimes as high as 0.5, okay? If you look at lasso, it's pretty much guessing x2 to be 0 almost every single time, okay? And if you look at ridge regression, with ridge regression, it's not pushing for 0. It says x2's coefficient is around 0.5, okay? But let's take a look at some of these summary statistics, okay? So for x2, the average coefficient here is, yeah, close to 0, -0.0267. Okay, so pretty close. But how much variance is there? There's kind of a lot of variance, 0.087. All right, so if you look at this, yeah, sometimes the x2 coefficient is pretty low, sometimes it's pretty high. So you got quite a bit more variance, 0.087. Okay, what about lasso? Okay, lasso, the average coefficient for lasso for x2 is also pretty close to 0, 0.022. Okay, so if you take the mean of all of this, we're getting something pretty close to 0, 0.022. Look at this variance. The variance is even less. It's super small, 0.0087. Okay, back here it was 0.087, and over here we're at 0.0087. So like 1/10 the amount of variance on the x2 coefficient is like 1/10 the size. Okay, for ridge regression, the mean of x2 is 0.49. That's pretty bad. Okay, it's a lot of bias. How much variance do we have? 0.04. Okay, so about half of the variance of OLS. So we reduce the variance, but we've got kind of a lot of bias here. Okay, and you can look at the other coefficients, not just x1 and x2. We kind of studied those more deeply here, but you can also look at x3 and x4, and you're going to see a similar pattern. And I think I have you guys do that in your homework. Okay, in your homework, I ask you to kind of look at the behavior of the lasso coefficients and the OLS coefficients and the ridge regression coefficients when you try fitting the same model to different random sets of data drawn from the population. Okay, and this all kind of helps us understand the bias-variance trade-off, right? The bias-variance trade-off is, how do we avoid underfitting and overfitting? And there's kind of this relationship. And if you kind of search online, what is the bias variance trade-off? You're going to see something like this. The expected prediction error as the bias squared plus the variance plus sigma squared. Okay, and there's a derivation of this equation on Wikipedia and stuff like that. Okay, the expected prediction error talks about refers to the idea of the kind of the squared error between actual values and predicted values for a new data set. Okay, so you fit a model and then you give it a new data set. What do we expect the prediction error to be? Okay, so that error is going to be the difference between the true value and the predicted value, and we square that, and then we're asking what's the expected value of that, right? What's the expected value? Expected value of, and this is going to be basically y itself is the true value plus some random error, right? True relationship plus random error minus the fitted values squared. Okay, and so the bias is the expected difference between the predicted values and the actual values. And the variance is basically the variance of the predicted values. Okay, and sigma, when we talk, so we have the bias, the variance of the predicted values, and sigma is just the standard deviation of the noise generated in the data. So that's just kind of unavoidable. To kind of illustrate this a little bit more, I'm going to go a little bit off track, and we're going to look at lowest regression. This is local regression. This is kind of a non-parametric method. And don't worry about the math behind lowest regression. The idea here is you have a couple terms, and one of them is how big of a window we want to use. Okay, so the idea of local regression is you have kind of like this moving window. So rather than looking at the full data set, so normally for linear regression, you look at the full data set and you say, what's the line that fits? What's the best fit line for the full data set? Local regression, you look at just a window of data points and you say, within this window, what's the best fit line I can fit on this window? Okay, and you kind of slide this window around. Okay, and so for this part of the graph, what's the best fit line? And it might be have negative slope, and for this part, maybe the data is a little bit more flat, and so it's a flat line, and over here you now have a positive slope or something. And so you're basically just, if I had to fit a linear regression right here, if I had to fit a linear regression right here on this window and right here on this window, and you kind of just slide that window around, and you kind of fit a local linear regression just on that local set of points, and then you kind of join them all together. That's basically what lowest regression does. Okay, and you have kind of like, how big of a window do you want? If your window is going to be like 80% of your data, and so you only kind of slide it around just a tiny bit, you're going to have a smoother fit. Okay, on the other hand, if you have just a very tiny window, a local regression of like 4 points, okay, your fitted line could these 4 points and these 4 points and these 4 points, you're going to have, you could have wildly different lines, and when you join them all together, you might get something that's very jagged. Okay, the extreme is just using only one value, and then you're just joining every single dot. Okay, and basically what we do is we make predictions by interpolating the values. Now R has a nice little low-s function that will perform local regression for us, and it joins them. Okay, so here's an example where and the true model is just this quadratic thing, x squared. That's the true model. I'm going to add so this is the true model, and I'm going to just add some random noise. Okay, I'm going to add some random noise, and so so what I've done here, the true model is this dotted red line. I've added some random noise to it, and I said, let's fit a straight line after I've added the random noise. Okay, and what do I get? This is the straight line. All right, It says the model that we produce is clearly wrong. At best, the linear model simply can't fit the quadratic function. But on the other hand, if I drew a new random sample and fit another linear model, we get a similar fit line. They will be a little bit different, but they're not going to be different by very much. Okay, so take a look at this. These, remember, I added random noise. The true relationship is this dotted line, and I've added random noise to generate my data. Okay, now I'm going to add different random noise, and I get these purple dots. Okay, so these purple dots and these gray dots, they're different, right? But the true relationship is still the same. And I fit a straight line to these purple dots, which is different from, slightly different from this blue line. So this blue line, purple line, slightly different. The gray dots and the purple dots are also slightly different, okay? And if I do this again, here is a set of dots. So these orange dots, different random noise from the purple dots. True relationship's the same, but because of randomness, I've got different dots. And so just imagine we had these dots and these dots. We fit the purple line to these ones. We fit the orange line to these dots, okay? And if I do this over and over and over again, okay, oh, and so if you compare all three of those lines, the blue line, the purple line, and the orange line, we can see, yeah, they're a little bit different. And they're different because we had different random dots. Okay, so what if I did this a whole bunch of times? What if I do this a whole bunch of times? So, let me get ahead of myself. Okay, if I do this a whole bunch of times with the straight, with the linear model, this is what I end up getting. Okay, this is what I end up getting. All right, so let me just kind of show on the other hand. On the other hand, I can fit a low S line with a tiny span. And so here I got these gray dots, and I'm going to fit a lowest line, and we can see this lowest curve, it fits these gray dots very, very well. Okay. Here I've got different dots, and I fit a low S, and this purple line fits those dots very, very well. And here are orange dots, and I fit the orange line to it, and it does a very good job fitting those lines as well. Okay. And if I compare those three lines, the blue and the orange and the purple, they're like wildly different from each other. They're wildly different from each other. All right. So here we have models that do a real good job of fitting their observed data, but they have a lot of variance from one model to another, right? If you look at, compare the, purple to the orange and to the blue, these are like wildly different lines, but each of them fit their own data super well. Okay. And so here I'm going to do the same thing, but I'm going to do this 100 times. 100 times. And so what I've done is I run these loops of code. And so this one is, if I fit 100, again, I took a random sample of data centered around the true model. And based on that random set of data, I fit a straight line. And so when we do that, yes, sometimes my lines end up bigger or lower, but the average of all of those things, okay, looks like this. And there's not a ton of variance from one line to another. They all kind of fit this neat little band here. These white dots in the middle here represent what is the average prediction across all 100 different straight lines that I fit. What is the average prediction across all 100 straight lines that I fit? And that's what these white dots in the middle represent. And we can see the average in the long run, there's a lot of bias in that these white dots do not align with the true model. The true model here is shown in black. That's this quadratic line, this curved fit That's the true model. And we can see the white dots do not match that very well. Okay. So that's what we have. Okay, the white dots do not fit the true relationship well. That means high bias. But on the other hand, the different colored straight lines, that is the different models that we fit, there's not a ton of variance between them. There's not a ton of variance between them. Excuse me, one moment, please. Okay, so high bias, low variance here, right? When you look at these straight lines, they're very similar to each other. Yes, there is difference, there is variation between them, but overall, the variance is quite small. This is the spaghetti that you get when you do low S, okay? So here, what's going on as far as this plot is showing is that we've got, remember, what I've done is I've generated a whole bunch of different data centered around the same true model. So the true model is in black here. And I generated random data points along this thing, okay? And I said fit a line to that thing. And so we have a whole bunch of different lines, and this is this colorful spaghetti that we get, right? But we said, okay, if you take the average of all of the different, spaghetti lines, take the average, that's this white dot here, okay? What is the average prediction right here? Okay, and it's this dot. What is the average prediction for this location? It's right here. What's the average prediction for this location? And if you look at those white dots, which is the average prediction made, we see that it is quite close to the true line, which shows up in black. It's not perfect. It's not perfect, right? If you look at the average of all of these lines is a little bit lower than the true relationship in black, okay? And the average of all of these lines is a little bit higher than the true relationship in black. But overall, I would say these white dots do a pretty good job of fitting the true relationship. The true relationship shown in this solid black line, I say does it. The white dots do an overall pretty good job of fitting it, okay? So that's where we have low bias, okay? Low bias. The white dots do fit the true relationship quite well, low bias. But if you look at all of these things, the lines, the individual spaghetti lines are drastically different from each other, right? We have high variance. And so the problem is that when you get one random set of data and you fit this thing, you don't know if you are this purple spaghetti line, which is like wildly off, or this light blue spaghetti line, which is wildly off, okay? It might be, it might be quite bad, okay? So you don't want that, right? You don't want that either, okay? So maybe you get something in between the two. Hopefully you can find something that has not a ton of bias, not a ton of variance, okay? And so this is low S where we fit. This is another kind of low S with a different amount of things. And so here, it's like tamer spaghetti, right? So if you look at this, the average, the white dots kind of follow the black line quite well. So we have fairly low bias, okay? How much do the spaghetti lines differ from each other? And overall, the spaghetti lines don't drastically differ from each other. This yellow line, this yellow spaghetti line is kind of the outlier, and it's like quite drastically different, and maybe we get some more variance down here. But overall, right, this looks kind of like neatly braided cord. The lines don't differ dramatically from each other as much as, like, say, this one does, okay? All right, and it's not as low variance as this, right? All of these lines are like very, very similar to each other. These lines aren't as similar. So there's a little bit more variance than the straight lines, but we've got a lot less bias, right? And so this is kind of what we want to achieve. We want to achieve some kind of balance between the bias and the variance. We don't want so much bias that the average of our predictions, these white dots, are going to be way off from the true relationship, okay? But we don't want so much variance that these lines are all like, each model is just like wildly different from another model based on the random data that you have, okay? We want something where, yeah, you get a random set of data, and sure, your line might be a little bit too high, your line might be a little bit too low. You're not quite sure, but you can be pretty confident that it's not going to be wildly different from someone else's, okay? Okay, and so that's kind of this idea of the bias variance trade-off, right? So you don't want to introduce too much bias. At the same time, you don't want your models to have so much variance that the model will drastically change or change dramatically with each random sample, okay? The tricky part is, these previous slides that we have were generated using a simulation. So I knew what the true values were and I could kind of compare that. In real life, you don't get to have a whole bunch of different random samples and you get to compare all of these things. Basically, you just get one random sample and you have to do your best with that, okay? And so, we do things like cross-validation to try to figure that out, but yeah, we don't get to do that at the moment, or in real life. I'm sorry, we don't know the true answers like we did in the simulation in real life. Okay, let's take a look at our next topic. Next topic is will be neural networks. Okay, so this is kind of a new shift, and so normally the break for neural networks happens like at a new week and in the regular school year, but because it's summer, I just got to kind of keep going here for a second. You know what? Let me give you your next view quiz answer, but I forgot what it was. So let me just pause for a second and let me look that up. Okay. The second view quiz answer is the letter C. The letter C as in cat. C as in cat is your second view quiz answer. C as in cat. Okay, and then I will just have to remember to give you your last view quiz answer before we end. Okay, I want to introduce neural networks. Neural networks are a popular topic. There is a ton of stuff out there on the internet about neural networks. I think these two playlists that I've linked here are probably the best videos that I have found on neural networks, okay? This one by 3 Blue 1 Brown is really, really good, okay? And this one by Welch Labs is also really great. The Welch Labs one, there's an example, and I'm going to kind of follow the simple example that they have, because he sets up this very simple neural network and leads us through all of the calculations in that one. And I'm going to kind of use that in the example slides. But the 3 Blue 1 Brown gives kind of maybe more of a better conceptual idea of this. So anyway, highly recommend that you watch both of these playlists, and you should like and subscribe to them. But anyway, all right. As far as this class goes, we will look at just the simplest kind of neural network. Now, technically, they've been around. They've been around since the 1970s and 1980s. And they gained a lot of kind of great popularity in the last decade or so, because our kind of computational power has caught up with kind of the power required for an effective neural network. And we use them most frequently for like image recognition and a lot of kind of AI systems. We are going to look at the simplest of the neural networks. And they're also an application of gradient descent And I just think they're neat. This is something that a lot of other 102B classes don't cover, but I think it's neat, and I think it's fun, and I think you'll gain something by looking at it. Okay. So what is a neural network? A neural network is basically just a way for us to design a function. And what is a function? A function takes an input, does some stuff to it, and it produces an output, right? So number goes in, or in this case, multiple numbers go in, stuff happens, a number pops out. That's a function. And the neural network just says, hey, let's mess with the numbers in kind of a complicated way, or just basically like, let's do a whole bunch of computations before we spit out a number. The inspiration for the neural network and why we call it a neural network is it was kind of inspired by the brain. You know, if you look at the brain, you got all these neurons, and they're all connected with different synapses. And kind of the way your brain works is that, well, I don't really know how the brain works, but if you look at a neuron, it receives inputs, you know, little input impulses, input signals. And sometimes based on the signals that come in, that neuron will activate. Okay, it'll send a pulse or an action potential, and it will send out this little electrical pulse to the neurons that it's connected to. Okay, and other cases, like the signals go in and that neuron doesn't activate, right? And that's how, like, you know, your doctors, they can hook up machines to your brain or your head, and they can see different parts of your brain activating, and they can say, oh, this region is receiving a bunch of stimulus and stuff. And yeah, I don't know, it's kind of a mystery to me. And here we're going to create basically an artificial version of this, a little neural network, and it's going to consist of different nodes, different, we can think of them as nodes. Input numbers come in, input values, and depending on the values that come in and kind of the node's activation function, the node will send out a new value to other nodes that it's connected to. Okay. So we're going to look at this very, very simple example. This is the example used in the Welch Labs video. And we have two input columns. Okay. And here he calls it hours of sleep and hours spent studying. And then we have one output, which is going to be a score we got on the exam. Okay. And our training data consists of only 3 observations. Okay, so we have n equal to 3. We have 2 x columns and 1 y value out. Okay, and you know, obviously, probably in a real data set, we would need more observations. Okay, but this is what we have. And kind of all neural networks will start with an input layer, and they all end with an output layer. And what we have is we have in our kind of our two columns in our input matrix, our input layer will have two nodes, one for each variable. And then our output layer will just have one node, which is the exam score. And a neural network can have one or more hidden layers. And for our network, we're going to just have only just one hidden layer. And arbitrarily, I'm going to pick our hidden layer to have 3 nodes. Okay, and this is a completely arbitrary decision, but I'm just picking a small number to keep this example easy, right? And all the nodes in each layer are connected to all the nodes in the next layer. So this is what our diagram looks like. I've got 2 nodes in the input layer, x1 and x2, all right? And these basically are just our 2 columns in x. And then I've got 3 nodes in the hidden layer, and each node is connected to each node in the next layer. So x1 is connected to all 3 nodes in the hidden layer. x2 is connected to all 3 nodes in the hidden layer, okay? And then the nodes in the hidden layer are connected to the output layer, okay? There's only 1 node in the output layer, so we've got 3 connections going from the hidden layer to the output layer. In this example, side note here, we have just one hidden layer, but you can have a whole bunch of hidden layers, okay? In the, where do they go? In the 3 blue, 1 brown videos, he builds a neural network with, I'm just gonna play an ad, won't it? Okay, well, you can kind of see this diagram. There's, he's got a bunch of nodes in the input layer, some nodes in the output layer, and he's got 2 nodes, or 2 layers, 2 hidden layers, okay, 2 hidden layers. We just have 1 hidden layer, but you can have a whole bunch. You can have like 100 hidden layers, or even more than that, okay? And because you have so many layers, we'd say this is a deep neural network or a deep learning model, okay? And deep neural networks and stuff are very powerful, and pretty much, well, you know, I don't know how magical these things seem to you, but now you can kind of, you can take a picture of something on your phone, and then later on you can say, oh, you know, show me all pictures of dogs, right? You can just, in your Photos app, you can just search for dog, and it's going to find pictures of dogs on your phone, which is amazing, okay? Because your phone is now, you know, using these neural networks to kind of classify and identify objects in your images, okay? And, you know, the idea of having a computer, you know, showing a picture to a computer and having it identify what it is, that was like the stuff of science fiction. You go back just a couple decades, but now it's something that we can do, right? And that's because a lot of work has been done, and there's this ImageNet data set, and there was like 14 million images, and there were like thousands of possible categories. You could say, oh, this is a picture of a butterfly, and this is a picture of a baseball, and this is a picture of something. And pretty much humans always beat the computers for the longest time, okay? And then I guess it's 7 years ago now. It feels it feels like it just happened, but yeah, it's already, I guess, 7 years ago now. A computer, a deep convolutional neural network, surpassed the human error rate, like outperformed humans, and it continues to get better, right? It's kind of like when, you know, computers beat humans in chess. Now the computers can outdo humans as far as identifying images, right? And here's like this little video on a computer taking image feed, video feed of, you know, from vehicles. And this is the next big application is creating self-driving cars. And I'm sure in just a few years, this will become like old hat, and you'll just be like, oh yeah, of course cars can drive each other. And why is this interesting? But this is like, it's cool. Okay. Now we're not going to do anything cool like this in this class. We're going to just, this is our neural network, not anything doing this, but the ideas, the basic ideas of how this goes, just builds up from here. Okay. Now, neural networks are really great as far as predictive performance. It is really good for making good predictions, but they are bad for like interpretability. You know, you take linear regression, you can easily interpret. You can say when x1 goes up by 1, you know, our prediction for y goes up by, you know, beta 1 and things like that. That's easy to interpret. Neural network, you say, hey, what does this node do? And we're like, I don't know. Okay. And it's kind of like, how does the brain work? We're not quite sure. Like, we know that certain parts of your brain do this and certain parts of your brain do that. But if somebody says, hey, what does this neuron do? We don't quite know. All right. But we know that the brain works. It's able to identify stuff and work, and we're able to think. But how exactly does it work? We're not quite sure, right? And as we make more and more deep neural networks, there might be like you know, like a neuroscience's study of the brains. There might be like neuroscience for neural networks, where we're like, okay, we've created this thing that's able to identify stuff, but what does this particular node do? And we might try to understand that. Okay, so anyway, let's go back to this neural network, and we're going to look at forward propagation, which is how values come in and move forward through the network. Okay, so in our network, if you look at how many arrows or how many connections we have, how many do we have? We have a total of 9. We've got 6 going from this one to this one, because I got 2 here and 3 here, and each one's connected. So I'm going to have 6 connections, 6 arrows going from the input layer to the hidden layer. And then going from the hidden layer to the output layer, I have 3 connections. Okay, so 6 connections from the input to the hidden layer, 3 connections from the hidden layer to the output layer. And each of those connections will have a weight, some number, okay, which is going to basically, you can think of how important is that connection. Now, again, don't try to interpret this and understand it at a deep level. We're not, this is just part of how the network gets trained to make predictions. So the training is, what weights do we use? What weights should we use? Okay, so I'm going to label each of these connections. All right, so the connection going from X1, and we're going to label the nodes in the hidden layer. We're going to call them Z1, Z2, and Z3. Okay, to go from X1 to Z1, I'm going to have weight W11. The connection that goes from X2 to Z1 is going to be called W21. The connection going from X1 to Z2 is W12. The connection going from X2 to Z2 is W22. And the connection going from X1 to Z3 is W13. And this one's going to be W23. Okay, so that tells you, the subscripts will tell you from where to where. Okay, they all have a kind of a superscript, a super 1, super 1, super 1. And this just means these are all the values that belong in the first set of weights. Okay, over here we have the second set of weights in orange, and these have the subscripts W11, the first node to the first node, W21, the second node to the first node. There's only one node here, so they're all going to have, they're all going to end in 1. But we've got W21 and W31, and they all have a super 2 because they're all in the second set of weights. Right? Is that notation okay? All right, so when I take these weights, I can arrange them in these matrices, right? So I'm going to have big W1, which is kind of the first matrix of weights, okay? And we have 2 rows, okay? 1 for each node in the input layer, and we have 3 columns, 1 for each node in the hidden layer. So again, we got W11, W12, and W13, and those are the ones that going from this first node to node 1, node 2, node 3, W11, W12, W13. And then in the second row, we got W21, W22, and W23. W21, W22, W23. And then as far as this one goes, I've got 3 nodes in the 3 rows, because I've got 3 nodes in the hidden layer, and they all go to 1 node in the output layer. Okay, so they are W11, W21, and W31. And they all have a superscript of 2 to indicate that they fill in the second set of weights. So how do we get the values Z? Well, we are going to take our X matrix, which has dimensions n by 2. Now, in our example, I only have 3 observations. So I have X is 3 by 2. But here I'm going to just say, in general, we have n observations. So it's n by 2. Our W matrix is 2 by 3. And therefore, when I multiply X by W, I'm going to get an n by 3 matrix. And you get an n by 3 matrix. Okay. And sorry, I hear my dog whimpering, but I'm not sure. Okay. Okay, so I have Z is going to be an n by 3 matrix. Okay, so I take x1, x11 gets multiplied by W11, x12 gets multiplied by W21, and that's going to form our first value in Z. This is going to be Z11. Okay, and then the next value in Z is going to be x11 times W11 and x11. I'm sorry, x11 times W12 and x12 times W22, and so on and so forth. And so I've tried to color coordinate this, and I did this all with LaTeX. I want you to just appreciate the work I did in making these LaTeX slides. Okay, with color, and then so anyway, now you have n rows, 3 columns. Okay, and then so we have the values. Now we do x times w, and we have these values in Z. And then what we do next is we're going to apply a function. We apply an activation function to each value in that Z matrix. Okay, and that's going to create the values. After we activate them, we're going to just rename these values to be A. Okay, so your Z matrix, after you apply a function to it, will just be A. So A has the same dimensions as Z. Okay, and so all we're doing is we're just applying some function element wise. Okay, so what function do we apply? Well, you have a choice of functions. The kind of classical choice of function is the sigmoid activation function. The sigmoid activation function is basically the logistic function. Which takes inputs anywhere from negative infinity to positive infinity, but its output goes from 0 to 1. It's basically the logistic function. Okay. Right. So, 1 over 1 plus e to the negative t, or it can also be thought of as e to the t over 1 plus e to the t. Okay. So if you have very large values, it asymptotically approaches 1, and for very negative values, asymptotically approaches 0. And at 0, you get 0.5, okay, like a logistic function. Now, the sigmoid activation function has fallen out of favor, and more popular is the rectified linear unit, the ReLU activation function. There's a whole bunch of other activation functions, such as you can go on Wikipedia, and they have a whole bunch of these different activation functions you can use. But yeah, logistic or sigmoid is kind of a classical choice. But we'll use it, even though maybe it has fallen out of favor, probably for its kind of historic popularity, we'll say. Okay, so let's keep going. Again, this is our thing. So we've got our Z's. I didn't write in the A's, but if you apply a function to all of the values here in Z, you're going to get your values A. And then what do? We take our A values and we're going to multiply it by our W. So A has the dimensions n by 3, and we're going to multiply it by our W2 matrix, which again only consists of these 3 weights, right? And they are arranged in a single column, 3 by 1. So even though it looks like a whole bunch of stuff here, when you multiply A times W, it's just one column of values. It's just one column of values, right? When you do n by 3 multiplied by 3 by 1, you do A11 times W11, A12 times W21, and A13 times W31, and you add those all together. This is just one value. Okay, this is just one value. This is just one value. So it's a column, just a column of one value, right? It's a single column, n by 1. And that's going to be your Z matrix, n by 1. Okay, and then finally, you apply another activation function. I mean, optional, but that's what we'll do here. We're going to apply an activation function to Z, and that's going to produce our predicted values y hat. Predicted values y hat. All right, and so this is what we have. It's x times w gives us z2. We apply f to z and we get a. We take a2 and we multiply by w2 to get z3. We apply f to z3 to get y hat. All right, so another way is, if you wanted to kind of nest all of these things together, you can have f of xw1 times w2. In this example, I'm using the same activation function, the same logistic or sigmoid activation function f, but there's, in general, there's not a requirement that they have to be the same function. So this could be some function g or h or something, right? You could have different functions here. In our example, I'm using the same activation function, that logistic sigmoid function, but in general, it's doesn't always have to be exactly the same. The Welch Labs video does not include a bias term, but a bias term basically adds a constant to each node before applying the activation function. So here you can add a constant. So you can do x times w1, and then you'll add a bias value b1. And then you'll do, x1, x11 times w12, and then you'll add a term b2 to it. Okay, so you'll have, in order to kind of make sure you're adding the same values, the same b values across all three nodes, we'll have to multiply it by a column of ones. Okay, so if you arrange you have one bias term, and so b1 is going to be basically a 3x1 matrix, and in order to kind of get this to work, I'm going to transpose it and I'm going to multiply it by a column of ones. And I'm just going to call this column of ones J, right? Because I is the identity matrix, which is usually a diagonal matrix of ones and everything else is 0. And so next to I is J, and this is just going to be a single column of ones. And this will allow the dimensions to work out. So if I have X, and I hope I apologize that the green color on LaTeX is this, I don't know how easy it is to see. It's kind of hard on my eyes, but I tried to pick a color here, but anyway, so x times w forms an n by 3. We get 3 columns. And then I'm going to take this column of ones and multiply it by b1 transpose, which is going to be a row vector or a row matrix of b's. And so this is going to also form an n by 3 matrix, right? So this is n by 3, and this multiplies out to be n by 3. And now I can add those two together, and this will form an n by 3 matrix, right? So we can see that x11 times w11 plus x12 times w21 plus the 1 times the b1, okay? And then for the next thing, we get this times this column, and we get that plus the b2, and then finally here we get the b3. Okay, n by 3 matrix here. All right, and again, well, I guess in your next homework, when you're dealing with the matrices, I strongly encourage you to write the dimensions of the matrix underneath each matrix. Otherwise, because if you didn't have this here, you would just feel like, oh yeah, I can multiply my X matrix by my W matrix, or my, but again, not every multiplication works out, right? If I didn't transpose the B here, I can't just multiply J and the B, because B would, would have an n by 1 times a 3 by 1. That's not going to work. So here I have to kind of transpose B to get this, okay, to get a 1 by 3. So always write the dimensions, and that way you can make sure that, n by 1 by 1 by 3, right? The number of columns on the left-hand matrix needs to match the number of rows on the right-hand matrix when you multiply them. Okay, we do the same thing for the output layer. So the output layer, They're coming in here, and I only have one node here, or one node and one bias term to add. So it looks like this. Now, just to kind of be consistent, I'm doing the transpose of this. Now, it's a scalar. I don't need to transpose it. But if you did have more than one term, then I am assuming your B's, you would keep them in a column, and then you'd want to transpose them to kind of work out. So it does make sense to transpose. But in this case, because it's a single scalar value, it feels a little silly to transpose, but here it is, okay? And again, when you multiply this row times this column matrix here, you get a single value plus, and then you have to kind of duplicate across all of the rows, 1 times B1. And so again, this is just a single value. And then all of these terms added together is also just a single value. And so we get a bunch of n by 1 matrix here. All right, and so if you kind of expand the whole thing out here, you have x times W1 plus j times B1 transpose, apply F to that, and then to get A2 times W2 plus j times B2 transpose gives you Z3, and apply F to that to get your y hats. Okay, and so this is our y hat. F of x W1 plus JB1 transpose times W2 plus JB2 transpose. Okay, so next up, we are going to calculate the loss function. And to see how good our weights are, we need to measure its performance using the loss function. And so our loss function is going to just be the sum of squared errors. We're going to just take the difference between the actual values and our predicted values, right? And we're gonna square them and sum them up. So I got y minus y transpose times y minus y hat, right? Y minus y hat transpose times y minus y hat will give us the sum of squared errors. And the y hats are given by all of this, okay? And so, I guess I'm going to finish a little bit early, but next week what we'll do is we will use gradient descent. We'll use gradient descent to find the gradient of this thing to find, to calculate the loss function. Now, let me talk a little bit, because I don't explicitly cover it in, I guess, in the lecture notes. But if you had to do gradient descent, because that's what I have on midterm topics here, I said numeric gradient calculation for the neural network, okay? So, we're going to start off with kind of this, we'll have something like this. And let's say I said, we want to calculate the gradient of the loss function with respect to one of these matrices, okay? So what would you do, okay? So let me just, all right, so here I've got x. We'll call this x. And this is n by 2, okay? So I've got x, let's just plug in some values. I don't know, 1, 1, and 1, 3, and 3, 1. Okay, all right. And then, so this is n, x is n by 2. And then we've got, so if we have 2 nodes and 3 nodes and 1 node, okay. Right. So W1 is going to be 2 by 3. All right, and let's just let's use the values 1, 2, 2, and 3, 1, 4. Okay. And then B1, let's use the values 0, 1, 0. And then we'll need a W2. W2 is 3 by 1. Let's keep this, let's use -1, 1, and 2. And then B2, let's just have a 1 there. Okay. All right, so forward feed, I would have to do XW. XW, what is this? Okay, so I'm going to have, it's going to be 3 by 3. Okay, so I'm going to go 1, 1 plus 1 plus 3, I get 4. And I get 2 plus 1, it's 3, and 2 and 4 is 6. Okay, 1 and 9 is 10. 2 and 3 is 5, and 2 and 12 is 14. And then I got 3 and 1 is, like 3 and 3 is 6. 6 and 1 is 7. And 6 and 4 is 10. Okay, did I do my multiplication correctly? Okay, and then XW plus JB1 transpose. So now I will add 0, 1, 0. So I'm going to have, so this column is going to be 4, 10, 6. This will be 4, 6, 8. And this will be 6, 14, 10. Is that okay? And then, okay, and then we're going to multiply this by -1, 1, 2. All right, so this will give me, oh, okay. Oh, I guess, and then I have to apply activation. All right, let's just, for simplicity, I think I wrote, for simplicity, the activation function will just be the identity. All right, so we'll just, the activation function is just the identity. I'm not going to, so a lot of times I would apply F to this, the sigmoid transform. I'm not going to bother with that. Okay. Now I'm going to just multiply this by the W2 matrix. Okay. So now -4 plus 4 plus 12 will give me 12. Okay. -10 plus 6 plus 14 gives me 10. -6 plus 8 and 10. Oh, wait. I have to multiply this by 2. So I did that wrong. Okay. 2 times 14 is 28. Okay. 10 minus 10 plus 6 is -4. 28 minus 4 is 24. -6 plus 8 is 2 plus 20 gives me 22. Okay. And then plus B2 transpose. I would basically add 1, 1, 1. So my final prediction, my y hats right now are 13, 25, and 23. Okay. So these are my y hats. Okay. Oh, I need an actual y. All right. So the actual y's, let's say, are 10, 20, and 26. So my loss, the loss is equal to y minus y hat squared summed up. So my loss would equal 13 minus 10, 9 plus 25 plus 9. I don't know what that is. 34, 43. This is my current loss. It's current loss. Is that okay? Save a copy somewhere. Where do I save this? Teaching 102B. Summer, week 2. Okay. So this is my current loss here. And okay, let's find the numeric gradient for, let's do it for W2. Okay, just keep it simple here. Okay, we're going to find the numeric gradient. How do I do the numeric gradient? So I'm going to, what I have to do, I'm going to just give myself some room here to work, is I'm going to add a small value to each of these things, but one at a time. Okay. So for this first iteration, I'm going to add a 0.01. So I'm going to do let's do a 0.1. Okay, so we'll add perturb by 0.1. Okay, I'm going to add a 0.1. So now I'm going to have negative 0.9 here. Negative 0.9 here. So what is the value I get? Here, I'm going to get 4 times negative 0.9 plus 4 plus 12. Okay, so I have 16 minus 3.6. So I will get 12.4. Okay, so 4 times negative 0.9. Here, let me pull up a calculator. Four times negative 0.9 plus 4 plus 12. Okay, yep, 12.4, right? Then I do the next one. 10 times negative 0.9, 10 times negative 0.9 plus 6 plus 2 times 14 plus 28, and I get 25. And then the last one will be 6 times negative 0.9 plus 8 plus 20. And this gives me 22.6. Right? And so after I do this, I'm going to get 13.4, 26, and 23.6. Okay. All right. And then so now my new loss will be 10 minus 13.4, so 3.4 squared plus 26 plus 6 squared plus the last one 26 and 23.6. What is that? 2.4? 2.4 squared. Okay, so my new loss is 3.4 squared plus 36 plus 2.4 squared. Okay, so my new loss is 53.32. Okay, so my change in loss it went from 43 to 53.32 is going to be my change in loss, I'm going to do 53.32 minus 43. And so that is 10.32. And change in loss, actually, so change in loss divided by size of perturbation. So 10.32 divided by 0.1 gives me 103.2. So that's going to be the first element of my numeric gradient. Okay. Now, how do I do it for the second element of my numeric gradient? Okay, second element of my numeric gradient. I leave the first value at -1, and then I add a 0.1 over here. So I'm going to get new values. Okay, so for the next element, I have -4 plus 4.4 plus 6. So -4 plus, oops, -4 plus 4.4 plus 6 times 2, 12. And this gives me 12.4. And then the next thing is going to be -10 plus 6.6 plus 28. And this gives me 24.6. And then the next one is -6 plus 8.8 plus 20. And this gives me 22.8. And then, so this will give me 13.4, 25.6, and 23.8. Okay, so I got so my new loss here is 3.4 plus 5.6 squared plus 2.2 squared. .2 squared. Okay, so let's try this out. Okay, I got 3.4 squared plus 5.6 squared plus 2.2 squared. Okay, and that gives me 47.76. Okay, and so that changed by -43. The original loss was 43, and it is now 47.76. So that changed by 4.76. If I divide by the size of my perturbation, I'm going to get 47.6. Okay, now I have one more of these things to do. But I don't know. Do you guys get the idea here? So now the last one, I'm going to do 2.1. Okay, I'm going to multiply this one by 2.1. And we're going to get new values here. So this last column, I get, what do I get? Okay, 4 and -4, 6 times 2.1. That's going to give me 12.6. Okay, so -10 plus 6, 14. No, this is too hard now. Okay, so -10 plus 6 plus 14 times 2.1. That is 25.4. Okay, and then here I have -6 plus 8 plus 10 times 2.1, 23. This gives me 23. Okay, and then now I add the ones, I add my biases. So I'm going to get new values. I get 13.6, 26.4, and 24. Okay. All right. And then so now I have to calculate my new loss values. So the true values are 10. And now I'm predicting 13.6. So my difference is 3.6 squared. The original true value is 20. I'm predicting 26.4. So my I'm going to do 6.4 squared, and then I have 26, and I'm predicting 24, so I'm going to have 2 squared. Okay. So now, what do I have? I've got 3.6 squared plus 6.4, whoops, 6.4 squared plus 2 squared, 4. Okay, and that gives me 57.92. All right, how much did my loss change? 57.92 minus the original loss of 43, 14.92, and then if I divide by 0.1, I get 149.2. Okay, so this is the estimate, my numeric gradient estimate. Ta-da! Okay. I hope that makes sense. All right. Well, it was recorded, and you can always kind of review this. But this is kind of a, well, I pretty much did the example problem for you. Okay. Numeric gradient calculation for a neural network. And I said I'll just keep it simple. So I'll have fewer nodes. So you don't have as many nodes. Even though this is pretty simple, we'll have even fewer. And you can try practicing this type of problem here. Feels like a 20-minute problem. Yeah, well, this one, because I had three values in here, okay? Because I had 3 values, it kind of stretched it out a little bit. So yeah, that was a little lengthier. I think on the actual exam, you'll have just maybe one fewer node, which I think will speed it up a little bit. Okay. Let me give you your last view quiz answer. Last view quiz answer is the letter E. E as in elephant. E. Okay. And that will be it. All right. Have a good weekend, and we will see you next week.